ngalakin kadijan yung boja.
All right, our fourth and final presenter is Mr. Omar Anwar. Omar completed the Bachelor of Science in Electronic Engineering in Pakistan and Masters of Science in Embedded System Engineering at the University of Leeds in the UK. Before starting his PhD at UWA Department of Electricals, Electronics and Computer Engineering, Omar worked as an academic and as a researcher at multiple universities. He is also the recipient of the WA's Government Science Industry PhD Fellowship, and today he will be presenting on remote beehive health monitoring using long-range communication. Please welcome Omar.
Hello everyone, welcome to the last presentation, and refreshments are just around the corner, so cheer up, you have almost made it. Okay, so as Dr. Amin mentioned, my work is on remote beehive health monitoring, and it is supervised by Dr. Gino, Adrian, Rachel, and Amitawa. My research is funded by CRC for honeybee products, and today I will be talking about some of the science which goes behind the art of beekeeping. Humans and honeybees, the story is not new. Egyptians had honeybees while they were building the Great Pyramids. Domestic bees have been with us for thousands of years, and why are we worried about them now? It is actually our survival, the human survival, which depends upon honeybees. Almost 1/3 of what we eat comes from pollination, and honeybees are the single most important pollinator. And recently they have not been doing very well. The fires and the climate change has adversely impacted a lot of their food resources. And then on top of that, there are some deadly diseases which can actually spread very fast and wipe out entire colonies. Domestic bees are very fragile and need a lot of care and attention. And beekeepers put in a lot of hard work to keep their bees safe. While inspecting the hives, they open the hive, they go through it frame by frame, and it takes a lot of time. Also, after every inspection, bees actually have to repair the hive from the inside. So we cannot do this inspection very regularly. Hives are often located far away in the fields for pollination or in the forest for collection of honey, and they are hundreds of kilometers away at times. So beekeepers have to travel these long distances to go to the hives and see if the bees are doing well or not. And after all this hard work, there's still a chance that they may miss something. There's a chance of manual oversight. Before we go any further, we actually have to understand the life cycle of a worker bee. It starts with a queen, the single most important bee inside a hive, whose only job in her 5 to 7 year life is to lay eggs, to breed. Eggs, they convert into larvae, and the pupate, this actually takes about 3 weeks, and after 3 weeks they hatch as hive bees. These hive bees stay inside the hive and do hive chores such as cleaning the hive, attending to the queen, to the brood, and maintaining the temperature. After about 3 weeks, these bees convert into foragers, and the only job of foragers is to go out and find food, which is pollen and nectar. The food they bring back, it is used by the hive bees, the brood, and it's also used to be stored to be used in the winter. After about 2 weeks of forager activity, the foragers die. So bees have a relatively short life cycle, from egg till death, about 8 weeks. The problem happens when environment starts to impact them. For example, harsh weather conditions can kill the brood, or if we are using some not suitable pesticides, that can kill the foragers. Or if there is no food to go around, foragers will not be able to bring anything back, and that can kill the hive bees. In a good healthy hive, the death rate at these stages, brood and hive bees, that is negligible. If we take a look inside the hive, this is a frame full of brood. All the brown part is brood which is ready to hatch. On top we can see some white cells which is cap nectar, and there is some pollen which is in yellow. Here are some bees which are hatching from the cells, and here's a frame which is full of cap nectar, or honey as we call it. So when it comes to electronic monitoring, there are 3 fundamental components these systems should have. Number 1, sensors placed inside or around the hive. Number 2, a communication system that should carry the data from sensors to the beekeeper, and a user interface which beekeeper can use to access this information. We have advanced components such as smart processing of the sensor data. We can have a network of sensors at a hive site. And we want long-distance monitoring, preferably global, where a beekeeper can access the status of the hive using internet from anytime, anywhere. And then there is health and status prediction, which is a hot research topic these days. The major aim of these systems is, number one, round-the-clock monitoring. Since we have sensors inside the hive 24/7, they can check the status of the hives continuously. And this actually increases the chances of disease detection, because we can pick them up timely. We don't have to wait for the inspection, which happens every week or every 2 weeks. We also expect these systems to not only tell us what is going on in the hive right now, but we also want them to warn us in advance if something bad is about to happen. So we want this prediction capability. What a beekeeper wants the most from these systems is to save time and money. And they will only invest in these systems if they will save them cost in the long run, which also means they want to minimize the use of labor. This brings us to the question of what sensors should we use inside the hives. So the first study of checking the temperature, monitoring the temperature inside the hive was conducted in 1917. And since then, a lot of sensors have been tested for their relevance with the bee health. Some are relevant, some are not. I have divided them into 3 different categories. We will actually be discussing temperature here. Temperature, a very high relevant parameter with very high relevance, because it provides us information about brood health and colony strength. For brood to hatch properly inside the hive, the temperature in the brood area should be 35 degrees centigrade. And bees work very hard to maintain this temperature. Let's assume this room is a hive and we are all bees, and we have to maintain a temperature of 35 degrees without any air conditioning. If it gets too hot inside the room, some of us will go out, open the door, and use our hands to make some airflow inside. That's hard work, right? But bees do exactly that. They go outside, they use their wings to cause a flow of air from outside the hive into the hive. This is called fanning. And if the temperature gets too cold, we will all cluster together. Provided there are no COVID restrictions, we will come into the middle of the room and use our body heat to keep the center warm. That is what bees do during cold days. They use body heat metabolism to generate heat and keep the brood warm. And this is only possible if bees are present in great numbers. If bees are healthy, if the hive is strong, they will be able to regulate their temperature to a steady 35 degrees centigrade. Otherwise, we will see variations. And what happens if the bees hatch at temperatures other than 35 degrees? Those bees have a problem. They are like bit like us, the academics. Disoriented, with little sense of direction. When they go outside, they spend a lot of time roaming around without actually knowing what they are doing. And at the end of the day, they bring back very little food. So a few of them are okay, but too many academic bees and the hive is doomed. So that's why it's very important to regulate the temperature of the hive. So is every sensor which is important, is it also practical? Unfortunately not. We have to look at a few different aspects to see if a sensor can be deployed or not. We will be discussing internal imaging in this case. On paper, it looks very good. Put a camera inside the hive and you are able to see what bees are doing. Job done. But practically, cameras do not work inside the hive. Number one, you need light inside the hive and it is very dark. If you put some light source, it becomes invasive and bees don't like that. Let's say somehow we get past this problem of light. Bees have this habit of putting wax on everything. So after a few days, the lens of camera is covered with wax. You cannot see anything. And cameras are also very power hungry. And if we want to process, extract information from the videos or images, it takes a lot of computation. So not everything which is relevant is also can be practical. So we have to find a good balance between relevance and practicality. Coming to our research, what we are trying to do? We are trying to answer 3 questions. Question number 1, how to classify beehive health state using data from multiple sensors. So we are investigating different sensors for their relevance, and we are also trying to find out which sensors complement each other well. If we are trying to record audio signals inside the hive, the microphones are very good at picking frequencies of 100 Hz and above. If we use accelerometers, they can actually detect low-end frequencies. And both of them put together give us a very good picture of the entire spectrum. Question number 2 is how to improve the classification accuracy given sensor limitations, practical constraints, and hostile hive environment. So we are testing different sensor configurations inside the hive while trying to find the right balance between cost, power, and practical feasibility. Question number 3, how to communicate hive data effectively over long distance for decision making. We are trying to find out what is the vital data from the hive that we should transmit, what should be the optimal sampling rate for the sensors, and what features should we extract inside the hive and how to transmit those features using least amount of power. There are many challenges associated with this work actually. Number 1, selection of parameters. As we have already seen, not everything which is relevant is also practical. There's also this question of cost versus accuracy. Good sensors, everyone wants to use them, but if they are costly, they are of no use because beekeepers do not want to spend a lot of money on these systems. So we have to choose sensors which are cost effective and work with whatever accuracy they have. Remote monitoring comes with its own set of challenges. Number 1 is power consumption. Out in the field or in the forest, there is no AC power available. So these systems should be efficient and they should last as long as possible using the small battery they have. Communication is another problem. The 3G or 4G coverage, if you move out 200 kilometers out, it is very patchy. It cannot be relied upon. If we go for satellite communication, it is expensive. NB-IoT, Narrow Band Internet of Things, it's a very good alternate. And here's the coverage map of Telstra for Australia. And this is very good coverage. But NB-IoT has a limitation. It cannot work with large amounts of data. So we have to have small amounts of data if we want to make use of narrowband Internet of Things. Okay, monitoring systems with decision-making capability. This is the most challenging task. We use machine learning, which actually works by going through examples containing both input and output. Input in our case is data which is coming from the sensors from inside the hive. Output is assessment of the beekeepers for the very same hive. And with enough examples, these machine learning models learn to translate sensor data into assessment of hive. This assessment which looks like assessment from a beekeeper. So these systems actually try to mimic the beekeeper. And this assessment from beekeepers, our ground truth, actually comes in forms like these. We have to actually ask beekeepers to fill out these forms whenever they are doing the inspection. And then we use the data collected from these forms to train our machine learning models. There is no publicly available training data set. Whatever data we need, we have to collect our own data so that we can collect our models. Coming to the progress. Okay, when we started, the first system I made was actually quite big, and it was meant to go into the middle of the hive, which beekeepers did not like because that is where the brood is. So now we have an improved system which is much smaller and it sits nicely on the side of a frame and it can be deployed and it does not get in the ways of bees that much. First system I designed, it died after 20 hours inside the hive. We don't want that. So after significant improvements, the new system can collect data for up to 20 days. And since we are using small solar panels, theoretically it can collect data forever because those solar panels keep it charging as we go. We are using feature extraction and reducing the sensor data size from 6,000 bytes to around 91 bytes. And this compression is vital because we want to make use of narrowband Internet of Things and LoRaWAN, long range wide area network. Both of them have good range, but they require data to be small. We have designed our onboards which have which can use actually both of these communication technologies. We are evaluating 9 different sensors in our design and more than 40 features for their usefulness with the bee monitoring. To conclude, it has been a journey of many findings. A lot of things I found out were about what does not work. A few of them, what does work. I have enjoyed excellent support from my supervisors, my funding body CRC for honeybee products, and the beekeepers I'm working with. And with their continued support, we hope to come up with a system which will be able to take better care of honeybees, hence improve the pollination and secure our global food supply. Thank you.
Thank you, Omar. Questions?